Welcome back to a new session of MOOC on Information Security. In this session, we will discuss the security of RSA. When we try to learn cryptography, we will come across the term RSA. What is RSA? The RSA is an abbreviation of Reversed Shamir-Edelman. These are the people who created the well-known RSA algorithm. The RSA technique is based on public key encryption, which is a public key crypto system that allows for secure data transfer. RSA algorithm is an asymmetric cryptography algorithm. Asymmetric key actually means that it works on two different keys, that is public key and private key. As the name describes, the public key is given to everyone and the private key is kept private. The idea of RSA is based on the fact that it is difficult to factorize a large integer. The public key consists of two numbers, where one number is multiplication of two large prime numbers, and private key is also derived from the same two prime numbers. So, if somebody can factorize the large number, the private key is compromised. Therefore, encryption strength totally lies on the key size, and if we double or triple the key size, the strength of encryption increases exponentially. RSA keys can be typically 1024 or 2048 bits long, but experts believe that 1024-bit keys could be broken in the near future. But till now, it seems to be an infeasible task. Security of RSA. RSA is a public key cryptographic algorithm that is widely used today to secure electronic data transfer. It is included as part of the web browsers from Microsoft and Netscape and is used by the SSL, that is Secure Socket Layer, which provides security and privacy over the internet. A public key crypto system uses a one-way function that is easy to compute in one direction and hard to compute in the reverse direction. For example, it is relatively easy to generate two prime numbers p, q and compute their product n equal to p into q. But given n, it is difficult to find its factors p and q. Encryption uses a public value or key which is distributed and known to anyone who wants to send a message. Decryption involves a related private key which is kept secret by the intent recipient and cannot be deduced from the public key. Public key cryptography works without requiring both parties involved to keep an agreed upon secret. The private key never needs to be sent to the sender. RSA's public key includes a number n, which is the product of two large prime numbers p and q. The strength of RSA comes from the fact that factoring large numbers is difficult. The best non-factoring methods are still very slow. For example, in a recent RSA challenge, which is in August 1999, a 512-bit RSA challenge number was factorized using 292 workstations and high-speed computers. The factoring took 35.7 CPU years to accomplish, which is equivalent to approximately 80,000 MIPS years. The feat required 3.7 months to calendar time because so many people have been trying to find efficient ways to factor large numbers. So far, without great success, we can probably assume that RSA is safe from a factoring attack for a typical key n of 1024 bits in length. RSA can be made more secure against factoring by increasing the key length to 2048 bits or more. However, there are many vulnerabilities exist in RSA algorithm. Different possible approaches to attacking RSA are as follows. Plain text attacks. The plain text attacks are classified into three subcategories as follows. Short message attack. In the short message attack, it can consider that attacker knows some blocks of plain text. If this assumption is true, the attackers can try encrypting each plain text block to view if it results into the non-cipher text. Therefore, it can avoid this short message attack. It is suggested that it can pad the plain text before encrypting it. Another one is cycling attack. In this attacker, suppose that the cipher text was acquired by doing some permutation on the plain text in some manner. If this assumption is true, thus the attacker can do the reverse procedure, which is to continuously do permutations on the non-cipher text to try and acquire the original plain text. The idea is that we encrypt the cipher text repeatedly, counting the iterations until the original text appears. This number of recycles will decrypt any cipher text. Again, this method is very slow, and for a large key, it is not a practical attack. A generalization of the attack allows the modules to be factored, and it works faster the majority of the time. But even this will still have difficulty when a large key is used. Also, the use of P strong prime aids the security. Unconcealed message attack. It is discovered in theory that in the case of some very limited plain text messages, encryption provides ciphertext which is the equal as the original plain text. If this appears, the original plain text message cannot be secret. Therefore, this attack is known as unconcealed message attack. Chosen cipher attack. During the chosen cipher text attack, a cryptanalyst can analyze any chosen ciphertext together with their corresponding plain text. His goal is to acquire a secret key or to get as many information about the attacked system as possible. The attacker has capability to make the victim, who obviously knows the secret key, decrypt any ciphertext and send him back the result. By analyzing the chosen ciphertext and the corresponding received plain text, the intruder tries to guess the secret key which has been used by the victim. Chosen ciphertext attacks are usually used for breaking systems with public key encryption. For example, early versions of the RSA ciphertext were vulnerable to such attacks. They are used less often for attacking systems protected by symmetric ciphers. Some self-synchronizing stream ciphers have been also attacked successfully in that way. Adaptive chosen ciphertext attack. The adaptive chosen ciphertext attack is a kind of chosen ciphertext attack during which an attacker can make the attacked system decrypt many different ciphertexts. This means that the new ciphertexts are created based on responses or plain text received previously. The attacker can request decrypting of many ciphertexts. There exist rather few practical adaptive chosen ciphertext attacks. This model is rather used for analyzing the security of a given system. Proving that this attack doesn't break the security confirms that any realistic chosen ciphertext attack will not succeed. Another one is guessing D. This time the attacker knows both the plain text and ciphertext. They simply has to encrypt something. Then try to crack the key to discover the private exponent D. This might involve trying every possible key in the system on the ciphertext until it returns to the original plain text. Once D has been discovered, it is easy to find the factors of n. Then the system has been broken completely and all further ciphertexts can be decrypted. The problem with this attack is that it is slow. There are an enormous number of possible Ds to try. This method is a factorizing algorithm as it allows us to factor n. Since factorizing is an intractable problem, we know this is very difficult. This method is not the fastest way to factorize n. Therefore, one is suggested to focus effort into using a more efficient algorithm specifically designed to factor n. Factorization attack. In factorization attack, the attacker impersonates the key owner, and with the help of the stolen cryptographic data, they decrypt sensitive data, bypass the security of the system. This attack occurs on an RSA cryptographic library which is used to generate RSA key. By doing this, attackers can have the private keys of n number of security tokens, smart cards, motherboard chipsets by having a target's public key. The entire security of RSA depends on the assumption that it is impossible for the attacker to factor the number n into two factors p and q. If the attacker is able to discover out p or q from the equation n equal to p into q, thus the attacker can discover out the private key. It is supposing that n is at least 300 digits long in decimal terms. The attacker cannot discover p and q simply. Therefore, the factorization attack fails. Attacks on encryption key. People well versed with the mathematics of RSA sometimes feel that it is quite easy because it can need a huge number for the public key or encryption key E. It also creates RSA more secure. Therefore, if it can decide to try and create the working of RSA faster by utilizing a small value for E, it can lead to potential attacks known as attacks on encryption key, and therefore it is suggested that it can use E as 2 raised to 16 plus 1, which is equal to 65,537 or a value nearer to this number. Attacks on decryption key. The attacks on the decryption key are as follows. Revealed decryption exponent attack. If the attacker can anyway assume the decryption key D, not only the ciphertext produced by encryption, the plain text with the corresponding encryption key E is in danger. But even future messages are also in vulnerability. It can avoid this revealed decryption exponent attack. It is suggested that the sender uses new values for P, Q, N and E as well. Low decryption exponent attack. It is fascinating to use a small value for decryption key D to create RSA work faster. This can provide the attacker in guessing the decryption key D by releasing the low decryption exponent attack. Brute force attacks. The first step in cracking the private key is to find the two prime numbers P and Q that were multiplied together to produce the modulus n. Determining phi of n gives n is equivalent to factoring n. With presently known algorithms, determining D given E and n appears to be at least as time consuming as the factoring problem. Since we can brute force crack a private key by factoring n, the security of RSA depends on how difficult it is to factor large numbers. Key size recommendations. To avoid values of n that may be factored more easily, the algorithm's inventors suggest the following constraints on P and Q. They are: P and Q should differ in length by only a few digits. Thus, both P and Q should be of the order of 1070 to 10,100. Both P minus 1 and Q minus 1 should contain a large prime number. GCD of P minus 1 and Q minus 1 should be small. Timing attacks. A timing attack is somewhat analogous to a burglar guessing the combination of a safe by observing how long it takes for someone to turn the dial from number to number. In this case, time for exponentiation may be used for attacking. Timing attacks exploit the timing variations in cryptographic operations. Because of performance optimizations, computations performed by a cryptographic algorithm often take different amounts of time depending on the input and the value of the secret parameter. If RSA private key operations can be timed reasonably accurately, in some cases statistical analysis can be applied to recover the secret key involved in the computations. There are simple countermeasures against timing attacks. Constant exponentiation time. Ensure that all exponentiations take the same time, but this will degrade performance. Random delay. Better performance could be achieved by adding a random delay to the exponentiation algorithm to confuse the timing attack. Blinding. Multiply the ciphertext by a random number before performing exponentiation. This process prevents the attacker from knowing what ciphertext bits are being processed inside the computer and therefore prevents the bit-by-bit analysis essential to the timing attack. RSA data security reports a 2 to 10% performance penalty for blinding. Protection against timing attacks. The basic idea to counter timing attacks is that we need to ensure information regarding execution time doesn't have a pattern that would enable the adversary to predict the key. In general, we can say that execution time shouldn't have any direct or indirect data dependency. In the case of RSA, we can use two techniques to avert time data dependency. Firstly, we can use a padding scheme called OAEP, Optimal Asymmetric Encryption Padding, which prevents chosen ciphertext attack. It refers to the analysis of plain text and the corresponding ciphertext of the concerned system. Then, a randomness algorithm is used before decryption to prevent non-fixed time computation in RSA. Other RSA vulnerabilities. While RSA naturally suffers from predictable vulnerabilities to brute force attacks at key recovery, its peculiar mathematical nature also make it vulnerable to other attacks. These include attacks against message confidentiality and attacks against public key generation techniques. Fortunately, we can generally defend against mathematical attacks by using RSA carefully. The practical result is that RSA must be used sparingly. When encrypting for confidentiality, it is best to limit the plain text to random, unpredictable data. RSA data security in RSA DSI has developed a set of standards for applying public key cryptography. These standards are called Public Key Cryptography Standards (PKCS) and are available from RSA DSI. Hence, in this module, we have seen several features of RSA algorithm, the possible attacks on RSA algorithm. Hope you enjoyed this session. See you next time. Bye.